All right, so prop 5, get some better lighting here, maybe. Prop 5 tells us something, gives us a nice, important, useful, well-known fact about isosceles triangles. Namely, and it's actually kind of a two-part claim. So, and this one's kind of cool because this one is purely just like actually a theorem. It's not even a construction theorem. It's not how to construct something. It's just stating something to be true of isosceles triangles, stating two different facts about isosceles triangles. So the proposition itself says in isosceles triangles, angles at the base are equal to one another, and if the equal straight lines be produced further, the angles under the base will be equal to one another. So it's saying, on the one hand, that these angles right here that are captured between the base of the isosceles triangle and the equal sides, these angles are the same. And more, if you were to produce these lines straight out, then the angles under under the base, like between the base and this extended line, those angles are also equal. Um, which for us, like that second piece kind of falls out from the first piece because we know that a straight line is equal to 180 degrees, which means that both of these being straight lines, if these internal angles right here are the same, then it means that their supplements must also be the same. But Euclid didn't have that machinery quite yet. He builds it up. All right, so let's run through this proof. I'm still kind of working out the kinks of my audio. I know it's been a little bit strange in the last couple videos, so I'm trying to get it a little bit better. That's why you keep seeing the cord to my earphones showing up. I'm trying to keep it out of the way as much as possible. All right. So ABC is our isosceles triangle with the sides AB equal to AC. Again, as far as the diagram goes, these little dashes, tick marks maybe are not traditional, but I put them in there just to make it really nice and obvious which sides are the equal sides. So the first thing that Euclid says is go ahead and extend out AB and AC. See if I can get that one a little bit better. Yeah, good enough. Okie dokie. So number one, extend AB and AC. And we know we can do that. That's just postulate 2. Says we can always do that. Any line that you're given, you can always make it longer. Okay, so next we're going to choose any point F. Specifically, choose some point F on BD. So these extended pieces, he says, well, just let D be something down here, and then this other side, the right-hand side, we'll call that E. So on BD specifically, so not on AD, but on BD, we choose our point F. So I'll take my point F to be about right here. I don't know, wherever you want it to be. All right. And then the next thing that we want to do is we want to cut let's see, what did they use? I think D, right? AE. Looks like we just, no, yeah, okay. Cut AE. I was thinking that we just didn't use D at all, but we did, of course. Cut AE equal to AF. And Euclid cites proposition 3 for this. So, and proposition 3 was the one that said if you have two unequal straight lines from the shorter one, from the longer one to cut off a segment equal to the shorter one. So our longer line is AE, the shorter line that we're looking at is AF, and he uses proposition 3 here to do that. Although personally, I feel that it's using a proposition, citing a proposition there is maybe overkill. Maybe I'm oversimplifying things, but it seems to me that all that we really have to do is make a circle of with center A and radius AF to create AE. Sorry, not AE, should be AG rather. Yep, sorry. I used E already. Sorry. AG. All right. So here's our AG equal to AF. Okie dokie. And then he says, all right, once we've done that, let's also construct lines FC and GB. So FC is right here. And GB is over here. We're doing this so that we can make some triangles because all the information, all the tools that we have so far are pretty much going to be, at least the powerful tools, are going to be tracing back to triangles that we can work with. All right, and this was, I guess, if we want to justify it, postulate 1. What comes next? Well, he says, notice that AF is equal to AG. That was by construction. AB is equal to AC. That's given to us. And, well, it's going to be some unfortunate lettering here, but basically he points out that angle FAG equals angle GAF. In other words, this top angle is equal to itself. Well, look at what we have. So we have this angle, or we have side AF, we have the angle A, and then we have side AC. So it forms this triangle. FAC, or maybe AFC, is one triangle. The other triangle that is formed is ABG. And from all of this, step 5, this is saying that those two triangles are the same because they have side angle side. They share side angle side. So FA is equal to GA. AB, or I should say, I guess, AC is equal to AB, and then the angle between them is the same. So this is sort of the triangle that we're looking at, the left triangle, and then the right triangle comes like this. So those triangles are the same. What lettering does he use? He said, then the triangle AFC is equal to the triangle AGB. Right. And so because of this, the remaining angles will be equal to the remaining angles, namely those which the equal sides subtend. So angle ACF is equal to angle ABG. So maybe I'll just kind of make that as a note. Angle ACF equals angle ABG. Yep. Because that kind of comes in handy a little bit later. Okay, and then the angle AFC equal to angle AGB. Yeah. Okay, no problem. Let's see, what else? What comes next? He says, and since the whole AF is equal to AG, and in these AB is equal to AC, the remainder BF is equal to the remainder CG. So, since AF is equal to AG by construction, and we know that AB is equal to AC, the remaining pieces must be equal. And that's common notion 3. I'll just kind of state it. So BF equals CG. This is common notion 3. Right. Or says, yeah, BF is equal to CG. Yep, there we go. But, he says, but but FC was also proved equal to GB. So FC was proved equal to GB. We just proved that on this step right here. Therefore, the two sides, BF, FC, so this side and this side are equal to CG and GB. And we proved, so let's see, BF, yep. So I should write these pieces out. We know, we saw this previously, is that FC is equal to GB. And this falls out from step 5. Same with the angle between them. So this angle CGB is equal to the angle BFC. And all of that is enough to state then that those two triangles are similar or congruent. It's again a side angle side situation. Right? So he says, but FC was also proved equal to GB, therefore the two sides BFFC are equal to the two sides CGGB respectively, and the angle BFC is equal to the angle CGB, so we have that these triangles are congruent. 6 steps. Wait, 1, 2, 3, 4, 5, 3. That's not right. Where did that come from? 6, and then this is 7. So these triangles are the same. Triangle BFC is congruent to triangle CGB. All right. Let's see, so from this we can conclude one thing at least. We can conclude that triangle FBC, angle FBC right here is equal to angle GCB. And that was one thing. That we needed to prove. This is saying the second part of this, where it says that the angles under the base are equal to each other. There, we just proved that. So this is angles under the base are equal. So we needed that. Well, what else do we need to prove? We still haven't proved that the angles at the bases at the base are equal. We still need to prove that, but we have everything that we need because we have proved that angle, what is it? Angle ABG, so angle ABG is equal to angle ACF. Where did we prove that? Well, it comes from step 5 here, that these triangles are the same. We get these angles are the same, so ABG, it's sort of this full angle of like the base plus this tiny little angle in here. So that's what we're looking at. Same thing on the other side. We've said that those are equal, but we also know that angle from this last step, that angle FBC, not angle FBC, rather angle GBC, is that what we said? So CBG, right, sorry. So CBG is equal to angle BCF. And this gives us that the angles at the bases are equal because angle ABG is equal to, so like, I guess just to make this a little bit more verbose, angle ABG is equal to angle ABC plus angle CBG, and angle ACF is equal to angle ACB plus angle BCF. But we just showed that CBG and BCF are the same. So, and since ABG and ACF are the same, we conclude then that angle ABC equals angle ACB. So, angles at base are equal. And that is what we set out to prove. Looks like things maybe got a little bit out of sync there. OBS. My OBS, I think, is trailing a little bit behind. I guess we'll see when things render. In any case, we have done being what it was required to do. Therefore, etc. is what my text says. Good enough.